Hi everybody, welcome to our next big unit actually in grade 12 physics. This is actually a pretty cool one I think because it's going to explain a lot of the neat things you might have been seeing around day to day. And it's going to build on some of the stuff you talked about in grade 10 science, the optics stuff. Now before you get too excited, we're looking at a different sort of optics. So instead of looking at what's called geometric optics, so things like ray diagrams, and lenses and mirrors, we're looking at another sort of more exciting side of optics. So we're looking at the what's called the wave nature of light, so sort of the wave particle, or sorry, the wave properties of light and how those sorts of things make some cool effects we see. So we'll explain some of these things you might have been seeing before. So you might have seen this sort of effects. Um, if you ever look at the ground, you've seen like a rainbowy color when there's oil spilled on water. Or looking at like a soap bubble. We'll kind of explain why that sort of happens. We'll talk about lasers. We'll talk about some cool patterns we can get by shining light through some simple things. And we'll look at again some some really cool sort of aspects of how light works, and really some of the mysterious ways of the way light works. But we'll start today with just looking at some of the basic properties of light, what we can observe about it, what we know about it, and let's start with what the heck is light. And before we get into what light is, let's look at a broader kind of question, this idea of the electromagnetic spectrum. And the electromagnetic spectrum, it's really this really huge range of waves. So remember, again, from grade 11, what a wave is, and we'll talk more about waves as we go through, but you should hopefully recall some of that stuff from grade 11. And all visible light is, it's just a really small section or a small subset of this whole electromagnetic spectrum. So my electromagnetic spectrum is this big sort of catch-all term for all sorts of electromagnetic waves, and visible light, the light that we see, it's just this spectrum or selection of it that our eyes can detect. And so all the EM waves though are going to be kind of the same sort of same idea, this electromagnetic wave. So what it actually is an electric field. So you can kind of see that one going here, this vertical wave, and at 90-degree angles to it, so that's kind of going into my computer screen here, is a magnetic field. And what you have is you have a constantly changing electric field. And if you remember from our fields unit, whenever the electric field changes, you get a magnetic field changing. And then whenever you get a magnetic field changing, you get an electric field changing. So actually you get this, what's called a self-propagating wave. The wave itself makes itself move. And this is kind of strange. But this is actually cool that light is actually, or at least I should say electromagnetic waves, don't need a medium. And as far as I know, they're the only wave that's true. Don't need a medium. So what that means is they don't need anything to travel through. They will travel through the empty of space. They're the only waves that will do that. Every other wave needs some sort of a substance to travel through. So sound waves travel through air. Usually we can have like earthquakes travel through the ground, but light actually will travel through nothing at all because it will actually propagate itself because this field, the electric field that changes will cause a magnetic field to change, and then the magnetic field that's changing causes electric field to change, and it will of course cause itself to propagate along further along. The distance between adjacent wave crests or wave troughs, we're going to call the wavelength, and it's given this symbol here. Again, that should look familiar from grade 11. That's the Greek letter lambda, and we're going to call that the wavelength. That's just a length, so we're going to measure it in meters. Just as a heads up, when we're talking about visible light, that's a very, very, very small distance generally. So we'll be talking about things like nanometers, micrometers, maybe picometers. So very, very small. So hopefully you'll be up on your metric prefixes by the end of this unit. All right, so what can make one type of light different from another? Really, there's only two options then, since they're all electromagnetic spectrum is going to be just different kinds of electromagnetic waves. There's really only two ways these waves can differ from each other. Um, and maybe before I get there, let me just maybe make a brief general statement here. I'm going to be using the word light interchangeably a lot with electromagnetic wave, um, just because I'm going to be a little bit lazy. Uh, but honestly, just because light is just a subset of electromagnetic spectrum, and really it's nothing special. It's just the one that our eyes are well suited to see. So anyways, light can differ from one another in really only one of two ways. One is the amplitude, or how high that wave is. And in terms of light, that will translate to is either the intensity or the brightness. So if you have a higher amplitude wave, you have a brighter wave. Or the other one that's actually a little more interesting is the wavelength. So if the length of the wave is longer or shorter, we'll have a different type of wave, or in terms of light, we'll have a different color of light. So let's scroll down to, again, something hopefully you've seen before. At the very least, you should have seen this in grade 10 science unit optics. The different sort of spectrum or gamut of waves you can get in the electromagnetic spectrum. So right in the, well, what we put in the middle often, because it's where we're certainly most interested, is the visible section. And I've blown it up over here for you. So we start over here with the right, or the red, pardon me, on this side. Over here on the other side is the violet or purple. And you go through that whole rainbow color: red, orange, yellow, green, blue, indigo, violet. Um, but you keep going past violet and you get ultraviolet, and it doesn't stop there. So this is where this graph kind of picks up. So after ultraviolet, you get X-rays and gamma rays, and you keep getting smaller and smaller and smaller waves. And on the other side of it, if you go past red, you get infrared or below red. Then microwave, the same kind of stuff that cooks your food in the microwave oven. You get radio waves, the same kind of stuff that actually sends signals across the earth. And so you get these other kinds of waves that are really, or sorry, the same kinds of waves, but just different wavelengths. And so again, the visible light is just this sort of subset of wavelengths or colors of light that we can see. And one of the neat things is that there's actually lots of organisms that are adapted to see other colors. So for instance, I believe that bees can actually see ultraviolet light. And they know this by looking at flowers. And again, hopefully, flowers are those cool colors to attract pollinators, one of the reasons anyways. Um, and if you look at flowers in ultraviolet spectrum, they're actually very colorful as well. And so then most likely bees can see those sorts of colors. And so their eyes are actually well suited to pick up ultraviolet light as well. So we only see these colors, but there's lots of other colors beyond those as well. All right. So let's just look at something else then. So we've talked about how these wavelengths can differ from each other, but something kind of related to that then is this idea of frequency. So again, hopefully remember from grade 11. But let's focus on just light for right now, or EM waves in general. And the nice thing is that in a vacuum, when there's nothing else around, no medium, no air, no water, no glass, no nothing, all EM waves, every single type, flavor, color, whatever you want to call it, they all travel at the same speed. And we're going to give that the symbol c, little c, universal constant. I don't know. That's probably why it's called little c. I don't know. But anyway, so little c, and we're going to call that, creatively enough, the speed of light. And the cool thing about the speed of light, it's actually one of those exact numbers. And it's exactly 299,792,458 meters per second. So that's an incredibly fast speed. That's how far light travels in 1 second. Um, Now, of course, we don't really want to punch all those numbers in our calculator, so we'll stick generally with 3 significant digits. And so here's our value of c we'll be using in our calculations. All right. So as I said, we can talk about speed and wavelength, but one of the kind of more fundamental ideas we want to talk about now is frequency. And you might remember that in grade 11, you looked at lots of examples when wavelength can change. So for instance, when a sound wave goes from one media to another, the wavelength will change, but frequency usually doesn't. So frequency often doesn't change for a wave, so that seems to be a more fundamental sort of quantity for it. And it certainly is for light, and we'll see why that is. So what we're going to do is we're going to try and use frequency sort of as our label for light as opposed to wavelength. So let's get away from how long the wave is right now and talk about how frequent the wave is. And the way we're going to do that is using the universal wave equation. So again, hoping you remember some of your stuff from grade 11. The universal wave equation is just v, which is the speed, is equal to the wavelength times the frequency, and that's again just given by our a consequence of just really kinematics and talking about lambda is the distance light travels, and frequency is how long it takes it to go that distance, or the inverse of it anyways. And so in terms of light, we can actually write this then as, since the speed is always the same as c is equal to lambda f. So there's kind of our universal wave equation for light. And so that's what we're going to have here. We'll put that in a nice little box. That's our universal wave equation for light. And so that's what we're going to be using here. And our frequency is what's going to be our label for different types of light, different colors, types, whatever you want to call it. So frequency, we're going to talk about so many hertz of light. All right, so let's do a quick example here. And my favorite color has a wavelength of 444 nanometers. Not 446, not 444, no, exactly 445 nanometers. And I want to know what is that frequency, and then we can look at what color that actually is as well. So hopefully, again, this isn't too difficult to get started. We know we're going to be looking with the universal wave equation, C equals lambda F. We've given you lambda here. Lambda is 445 nanometers. But the obvious question is, how big is a nanometer? Again, nano is one of those basic SI prefixes, which means 10 to the minus 9. So what we have is 445 times 10 to the minus 9 meters. And C, again, is 3 times 10 to the power of 8. So I trust that you guys can actually do that calculation on your own. But what I'm getting for frequency is 6.74 by 10 to the 14 hertz. So that's an incredibly high frequency in terms of everyday language anyways. A very, very frequent wave. So that's traveling or have a lot of cycles per second. And in terms of what color that would be, we'd have to look that up unless you've memorized all the colors already. But luckily I've got a table here. They've listed their frequencies in terahertz. Tera is 10 to the minus 12. So we can write this frequency. We could also write it. Got the pen back on. We could write this frequency as well if we wanted to as 674 terahertz. So 674 terahertz puts it right in the sort of blue violety range, just on the edge of violets. If you were Newton, you'd probably call that indigo. So there's, I guess, my favorite color. All right, and so let's just take a look at some pretty cool applications of this. And so one of the kind of neat applications is the sun and our atmosphere. So the first graph up here we're looking at here, this is actually the orangish line. This is the spectrum the sun puts out itself. So if we were up in space measuring all the intensity of the sun, this is all the different colors, or at least the spectrum the sun puts out. And down at the bottom here, you might guess at what this number actually represents. This is going to be the measure of the wavelength. So not frequency, but wavelength. And over here up the top, we've got increasing flux, which is really just a way of measuring the intensity. So the higher the number, the more intense light, or the more light is coming down. And so the sun would actually peak, have the most intense light up in space, somewhere in the kind of bluish range. And if you remember from grade 10 optics, though, what your brain does is it actually combines all these colors together and comes up with a nice sort of yellowish color that we're going to see. So that's our brain sort of doing that for us. But the other thing to keep in mind is that it's not just up in space we're seeing it, that in order to get to our eyes, the sun actually has to go through our atmosphere. And so we're seeing some certainly drops in the sun's spectrum. And what I think is kind of neat, if you look, there's these huge sort of dips. Like there's a dip right here, there's a dip right here, there's these dips at these different spots where you get these sort of big gaps where there's no sort of sun's intensity. So the sun follows this sort of nice smooth curve up in space, but when it gets to us down on the surface, we're actually losing a lot of these colors. Now, a lot of them in this graph are the infrared, but there's certainly some in the visible as well. And this has to do with atomic absorption and the idea of where electrons are. And we'll talk more about this a little bit as we get further on in this course. But really what's happening is different electrons at different orbital heights are absorbing these different frequencies or wavelengths of light. And so they're actually being kind of absorbed by the atmosphere, not making it all the way down. And kind of like how you can tell what a star is made of by seeing what elements it's not emitting, we can see what our atmosphere is made of by the elements that it's, or by the lights that it's absorbing. And something else that I think is kind of another tie into bio You might say, okay, well, how come I can actually see the visible spectrum? Why don't we see ultraviolet? Why don't we see infrared? Well, it makes sense when you see where's the most intense light actually coming and hitting us. It's in the visible spectrum. So the reason our eyes can pick up the visible spectrum and not infrared, well, that's where most of the light is. It'd be pretty stupid if our eyes could only see ultraviolet because we wouldn't be able to see much. It'd be really dark all the time. Same with the infrared. Our eyes are well suited to see the visible spectrum because that's where most of the light is coming in. And I think that's a pretty neat observation to make. All right, and the other one that I think is kind of neat related to this, same sort of idea with the atmosphere absorbing um, different colors, is how do you actually absorb or explore space? How do you look at things that are far away? So if you certainly look up at the sky, you're using the visible spectrum, and so you're kind of limited to what you can see with your eye. But of course, astronomers want to use all sorts of different frequencies. They want to look in radio waves, ultraviolet, gamma rays, all sorts of different spectra to see how things look in different frequencies. Um, and they're very concerned with what the atmosphere is doing. And so one of the measurements we look at is this thing called atmospheric opacity. 0% meaning it lets all of the light in at that wavelength, and 100% meaning no light comes in at all. It's completely opaque at that wavelength. So what this means is everything sort of with a wavelength less than 100 nanometers, our atmosphere blocks out entirely. So if you want to see the universe in any sort of wavelength below that, you've got to go to space. Same with any sort of frequency, or sorry, wavelength above around 10 meters. You've got to go to space. There's this nice sort of open window here um, in this sort of range where there's lots of different wavelengths where radio waves are observable. And this is where a lot of radio work is being done from Earth. So if you ever see any sort of large radio telescope set up on Earth, this is probably the range they're set up in, just because this is the range that's actually very useful um, for actually doing ground-based observations. Anything else that's outside of this range, you'll have to go to space to do. So any sort of large like X-ray telescopes, things like that, have to be up in space because they'd be kind of pointless down on Earth since the atmosphere would block out most of that good light coming in from space. All right, so I think that's it from today. So hopefully not anything too challenging, just a brief overview of what light is and how it sort of works. And we'll look at again some of these cooler pictures, like on the picture on the front sort of slide here, on what the stuff's all about. But I hope that makes sense. And any questions, you can talk about them in class, and we'll pick up from where we left off next time. Hope you have a good night, I guess.